let's get started. So thanks for coming. So I'm gonna give you a bunch of demos and a bunch of results and how the theory is implemented. And I'm also going to talk a little bit about how like what I want to do with it in the future, or what I believe to be possible in the future. So first of all, there's a link to my repository, and there you can find links to the wiki, and I've also written a bunch of blog posts that go in much more detail. So it's I haven't updated that in a while, but I think the information is still relevant, let's say. So most of that didn't change since I last updated it. And yeah, so I'm kind of looking at a bunch of different chat channels. So if you don't have a Twitch account, just ping me wherever I am, basically. So I think that should be fine. Okay, so first of all, like, why did I want to do this? And I was a couple of years, or like, let's say 1 year ago, 2 years ago, I was working with Coq a lot, and I ran into a bunch of issues that, well, I didn't really know how to resolve within Coq. And after thinking about these issues that I had for a while, at some point I realized that all of the things that I was lacking, or that Coq was lacking in my opinion, could be implemented if Coq had more powerful metaprogramming features. And so I kind of set out, first of all, to try to define the things I need, and what metaprogramming features exactly I needed to get there. And then I also, like, when I started looking into it a bit more deeply, then there's of course the issue that Coq is incredibly large, and like you can already see that if you look at the Coq documentation. Like, I don't mean large necessarily in terms of how much code there is. That's also of course an issue, but Coq is also incredibly large in the sense that it has tons of features. And if you want to understand, like, if you really want to use Coq, then there's a huge amount of stuff to learn. And that, I mean, of course, it's nice that the stuff is available, but to me, it feels like it has a similar problem to what Haskell has, where Haskell has this, I don't know, hundreds of language extensions or something, and, well, you have to, you don't have to learn them all, but there's this huge fragmentation, basically, and it's a bit annoying, right? And of course, over time, this fragmentation will only grow. Well, and then at some point I watched a talk about Hackett, which is basically a language that is very or that wants to have like a Haskell type theory, but a Lisp or Racket metaprogramming system. And well, it's built in Racket. That's really nice. And I looked at this for a while, and of course, one issue was that there were no plans to add metaprogramming. And the other issue is that at some point I realized, or at least I think I realized, because it wasn't really that properly documented, but I think if you want to do metaprogramming in Hackett, then you don't get you don't have the same typed system in Hackett. So I think you get a completely different syntax, or well, not completely different, but yeah, it's the metaprogramming language of Hackett is not the same as the regular language. I think. I'm not sure about that. So those were a couple of things that annoyed me, and after watching a talk about implementing dependent type theories yourself, I kind of grew some motivation to actually do this, and well, then yeah, it just went from there. All right, so let's actually start out with a bunch of results, because I think that gives you a really good overview of like why I'm doing these things and what's really the thing that I want, right? So first of all, if you do, for example, metaprogramming in Agda, I really like metaprogramming in Agda, but there are just things that you can't really do. I think an example is you can't use pragmas. Might be wrong about that, but I think you can't use write pragmas onto your code in Agda. That's but that's just an example. Like in most of those languages, I kind of observed that you always your metaprogramming always stops somewhere, and that's I wanted to avoid that. And so yeah, that's one thing that you have in Meta Cedille. Everything that you can write as code by hand, you can generate with metaprogramming. And then the other thing that that I needed, or that I really wanted to have, was to basically be able to do definitions of syntax as you do in math, right? Where in math you don't need to write, or you don't need to have a fixed syntax for natural numbers, right? You can start your book or whatever on logic without a notation for a natural number or anything, and you can just define it at some point, and that's fine. So that it took me a while to figure this out properly, or in a way that I found satisfactory, but you can in Meta Cedille write arbitrary LL1 grammars right now. So there's also a way you can actually do arbitrary grammars, and I mean really arbitrary, like context sensitive, whatever. but that's a bit more complicated. And I have a simple example of a context-sensitive grammar, but it's like really basic, and there needs to be like a proper framework for this to really be feasible. All right. So so moving on from that very general feature overview, the theory I built this upon is very, very small, and the basic system has like almost no features, and so I basically every let's say real feature that you would expect in a programming language, I just implemented with metaprogramming. So like the first example is just the notation for data types. Basically just your standard syntax. That's possible, and I have example code for that. Then data types and records. So currently that's not a full implementation. You don't get recursion and induction right now, but that's not there is no technical reason. It's just not done yet. It's a lot of work. And then also actually a module system. So when you actually start up the environment, there's no notion of module, or you can't even undo definitions, for example. So like you can't really, if you wrote a wrong definition, in the sense that you later discover that you want to change it, then you have to restart the environment. But with the module system, so the way the module system is, let's say, planned, I half implemented this at this point, but you with that module system you kind of get to reload modules and reload definitions. It basically works by setting up temporary namespaces and so on, and then later on you just choose a different temporary namespace, and that way you get kind of the illusion of reloading without actually breaking anything. And then there's a bunch of things that so module system is also implemented at this point, but again the reloading mechanism is not fully implemented, but a bunch of other things are, and I'm going to show that later. And then a bunch of things that are similar in that regard, but where I didn't get to do anything about it, is inference for implicit arguments and type classes, of course, or instance arguments, if you like, or whatever, or like in general, well, not in general, but like the ability to solve unification problems. These kinds of things are definitely possible, and I can actually show you later on like why I'm so certain it's possible. And well, then also something that I kind of miss in Acta is Haskell's deriving feature. I mean, you can of course do something with Acta metaprogramming, but it's not as nice, right? I mean, in Haskell it also has its problems, where you only like you only get the nice syntax with the built-in deriving stuff, which is of course also not the best. Yeah, and so what really the advantage is here is that as soon as all of these features just live in some library instead of in the compiler, let's say, if you want to call it that, then you really can compete on these features, right? You can implement a competing module system mechanism, for example, and well, of course, you then want to like get compatibility or something somehow, but there's no reason, for example, if at some point it's discovered that there is a better way to do module systems, which I think, like depending on what kind of module system you're talking about, there are already good and bad ways, so by doing that, you can just if you have a good idea, you can just implement it, publish the library, and everybody gets to use it without having to wait until you got, for example, the new Agda release or something. And of course, I think there's a point to make here about that you don't, or it might be a good idea to actually have multiple competing systems at the same time. Maybe not for module systems, but for example, I see no reason why unification algorithms or something like that, why there should be one true algorithm that you're supposed to use. And so if you are able to just load a unification algorithm from a library, then you kind of open up the space, and I don't know, maybe there's a great unification algorithm that works in linear algebra but doesn't work anywhere else. Like, how would we know, right? These things are really difficult to test, but if you are able to just load one from a library and even use multiple ones without like getting problems because of that, I think that's a really nice addition to the language. Okay, and then I also have a bunch of stuff that's, I would say, new in the sense that I haven't really seen it in other languages. So the first of that is the ability to get some additional state in your system. So, for example, like a simple example would be if you want to add a new flag, for example, that you can just set, like enable or disable or something, and then, like, depending on whether that flag is enabled or disabled, you can, for example, do different things in your metaprogramming. Like, that's a really simple way of doing this, but there are also more complicated examples, and I'm using that actually very heavily. So the module system uses this, and also the next point about internal logics, that's also using this feature. So that's really useful. And yeah, you can basically record any data of any type in there. And that's not like something that I built in. That's just a consequence of how the metaprogramming works. I'll show that later. Yeah, and then that's something that I finished very recently. There's actually still one bug, which is why I haven't pushed it yet to GitHub. But I think I know what's going on, and I just didn't get around. There's a question. Are there plans to implement tactics with this data metaprogramming system? Yes. So tactics require, of course, can say of course, but not sure if that's so obvious. Tactics require some unification algorithms, which, as I said before, are not yet implemented. But as soon as I have some simple unification algorithms, I'm probably gonna play around with a few simple tactic features. So yeah. Okay. So yeah, I've implemented an internal logic. So my example code is just a regular calculus of constructions, nothing fancy. And the point about this is that you can just write regular code that, instead of being type checked against your regular outer logic, let's say, that code just gets type checked against this inner calculus of constructions that's been formalized in there. And then there's also, because I'm using this this state system, I can just have an environment for that calculus of constructions, and then I can just define terms in that calculus of constructions, and well, basically just program regularly in that internal calculus of constructions. And of course, as soon as you do that, you can there's actually the way this works is you by basically converting the terms of the outer system into terms of the inner system. That might fail, of course, but then you just give an error message. And so there's actually like a really simple path of now getting to infinitely nest these calculus of constructions, because you can just take the definition and the functions and so on that have been written and just put them into the new logic, and then you can work in an arbitrarily deep calculus of constructions without basically any syntactic overhead. And another nice thing that you get from this is you can use, for example, setoid type theory, which I think gets its name from the Coq bug tracker. I couldn't find any other reference of that exact name, but using that you can basically pretend quotients exist by whenever you want to refer to a set, you actually replace it with the setoid with a trivial equivalence relation, and then you get to define sets or types or whatever you would call them in that context, basically also with an equivalence relation of equality, and then from there you can basically by redefining a bunch of syntax and using a bunch of automation to skip unnecessary proofs where your all the setoids involved are trivial setoids with a trivial equivalence relation, then you just get to basically pretend you have quotients. So that again also relies on some proof automation, for which you really need some unification stuff, or I think in some cases you don't need unification there, but you still need a bit more than what is currently implemented to actually do this, but I see basically no reason why this shouldn't just work. And then you can also basically just fully switch to an internal logic, right? If you decide I have a file and I want this file to be entirely in my internal calculus of constructions, you can basically so you already get to use the original syntax, but basically at the beginning you're using a slightly different invocation to tell the system, well, this is supposed to be a term in the calculus of constructions, not a regular definition. And basically by just removing this little piece of syntax and just using the one that you originally had, you basically can just fully live in this internalized logic. Okay, so I talked a lot, and let's show something. So I need to clear this. Okay, so the first thing I kind of want to show is the difference between the original syntax that you get when you originally start the system. This is actually not a built-in syntax, depending on your definition of built-in. So even the initial syntax is in no way special or more special than any other syntax, and can completely be overwritten. It's just a bootstrapping problem where if you don't have syntax, how are you going to define new syntax, right? So you need some form of initial environment that gives you an initial syntax. And so, like, for example, if you look here, this little piece is function application. So in the original syntax, you only have binary function application, and the binary function application is denoted by these brackets. So you kind of get a lot of brackets. Like here, I basically apply this function bind meta to 4 arguments. There's in Cedille you have erased and non-erased arguments, and you have to specify what kind of arguments you're talking about. Usually, like if you want to work with that like you would work in any other regular calculus of constructions, you can just have every argument non-erased and basically be fine, except like very special cases. So here, like, you get a ton of brackets because there is no proper syntax for it. And then if you load the some of the files that I've already provided in there, then you get to use the syntax down here. And so you can already see it's a lot nicer in many regards. So you have, for example, this OCaml or ML or whatever notation of you don't need to put the lambdas at the beginning, but instead you put the things in a bunch of brackets, and then at the end you declare the type of what you're going to define under these lambdas, and this type annotation will, for example, actually be desugared into the longer type annotation that you can basically see here, where you have to explicitly put a new line. So that's the type annotation here. And so you can automatically recover this in this case, for example. And then you can also see this bind meta, can now just be applied to stuff with a regular syntax, where, well, it's almost regular. There are these question marks in there. They again correspond to a raised application. So yeah, that works kind of nicely. And then, I mean, I can, oops. For example, run this, and then you already see that, like here, you get basically the previous definition of the spine meta, except that I'm printing the De Bruijn indices here because my internal representation doesn't have names right now. That's kind of annoying. I want to fix that at some point so that this printed stuff is a little bit nicer. But yeah, that's not really a big deal. Okay, so that's just what you can do from like, or yeah, what kind of different syntax you can actually achieve with this. And so this is also like a very simple example where, yeah, as I said previously, there is no built-in notation for strings, lists, or natural numbers, and you can see all three of them used here. So yeah, I could now point to all the files defining the syntax. But yeah, that's just a lot of stuff to look at. And we can also do the module system. So here you see that there's a bunch of stuff happening already just by entering a module. That's basically because I need to record a bunch of metadata about that module. And every time I make a definition or some change about that module, I also need to record more metadata. And well, there's only one way to store data, right? You define that data somewhere, and that's why I'm always defining a bunch of extra stuff all the time. Like you can also see here that I get a second line for that. And of course, we end the module, do a bunch more stuff, and yeah, and now we get to use it. So let's enter a new module and import the previous one. And you can see that now I have defined this A that I defined previously, but this time, so if you look up here, I just annotated it with a single star, so A is just a type. But down here, I'm now getting type to type. Oops. And that works. And for some reason takes a bit. So yeah. There are a few things about modules that don't work the way you would expect it right now, but in general the stuff works. And let's also show data types. So this takes a bit longer. Oh, actually it doesn't. Interesting. I wonder why. Last time I checked, this took a bit longer. Oh, I think I know why. Okay, doesn't matter. Yeah, so you can see there's a bunch of stuff happening from this data type. So I'm defining a bunch of functors or like one functor and a bunch of other stuff. And basically what it does is it generates the data type for you, it generates the constructors, and it generates a fold that's here. So you can use that fold to map from lists to somewhere else, and you can, for example, define recursion from there. So recursion is kind of it's a bit annoying to do by hand, but it's not too difficult. Of course, at some point I want to automatically derive these things and maybe even have nice syntax instead of having to use folds for that. But that's without like a better automation system that I have to build first. That's a bit annoying, so that's still a little bit off. But yeah, from that you can just invoke constructors regularly and use your folds and I don't know, define the reverse function or something. So that's all possible. Yeah, and then of course I want to show the calculated constructions. Hope this works. This is very new. Okay, great. So now you see there's also a bunch of stuff happening. And this guy here is the environment that we're defining. Well, we start with a zero environment, basically, like an empty environment, and then we apply a function here that just converts that. And the thing is, if this definition failed to type check, then we wouldn't define anything. Right? We would get an error message. So I don't know. Let's do this, for example, and then you get an error message, and yeah. Right, and then of course I want to show that you can actually use this now, and yeah, you can now refer to the previously defined identity function in your fancy new identity prime. Yeah, as I said, there is still one bug remaining in, I think it's in the checker for beta equality. So some stuff doesn't work right now, but I should be able to fix that soon. All right. So how does it work? Well, it's actually not that difficult. So first of all, what you do is we take our Cedille core, or we can also use some calculus of inductive constructions, or some other constructive type theory, doesn't really matter. And we extend it with a metaprogramming monad. That's basically all that's happening here. So if you if you look at the first rule, that's just defining the metaprogramming monad basically. Then you have an epsilon and a mu for the two monad operations. That's I think pretty much standard. And then there's this fourth rule here that gives you basically access to a bunch of features in this monad. So the idea here is that I have these, I pick a natural number, big N, and just take a set of symbols, M1 to Mn or something. And also, so these are just symbols, the Mi. Si and Ri are just regular terms. And the general idea is that basically this xi mi is supposed to be a function from Si to M Ri applied to T. And it's basically just a catch-all rule for a bunch of stuff. So, for example, I think. So, for example, what you do in here is defining terms in the environment. Right? If you do a let definition, then there is an M that corresponds to that definition, and the S there would be you give it a name, term, and then the result would be like a potential error message, for example. I don't know right now what I'm actually using in the current implementation, but you could, for example, return a type of maybe string or something to give an error message in case it failed, or nothing in case you got a success, something like that. And a different thing would be, for example, you can there is also an M that lets you do calls to your system shell. So you saw this echo command I did a while ago, where I printed that string. That's actually, there is no printing functionality in Meta Cedille. That's implemented via calling out to the system shell and calling the system shell's echo. It's probably inefficient, but I mean, I think it's a cute, fun thing to do. Yeah. So these kinds of things live in there, and basically, so the intuitive reason why these things don't hurt your theory, in the sense that it doesn't let you do anything that's false, is just because this is always wrapped in this monad, right? And there's basically no way of getting out of the monad. I actually have a proof that doesn't work like that, sadly, but that's like the intuitive reason why it should work. Yeah, okay. So that's the type theory, like that's all. So how do we do this whole syntax magic? And the way we're doing this is by adding a meta environment. That meta environment contains parsing rules, essentially, and to each parsing rule you also associate a term, like a regular term in your language. So that's in the meta environment, and then there's also a special term that's supposed to be the evaluator. And I'm gonna go into what these things do and why they are there in a second. One thing that I want to mention is that you can't read anything from the meta environment. So like technically there's no reason why you shouldn't be able to read from the meta environment in inside of the meta monad, but there is also no real reason why you would do that, because basically you can always you can always make a copy of that meta environment and just carry it around with you, like we did with the environment for the calculus of constructions, right? So you could do exactly the same thing. It's of course less efficient, but yeah, there's no real reason why you need to do this, and there's actually a big advantage because then you don't need to deal with you don't really need to deal with some ugly types and stuff that happens when you actually want to talk directly to the meta environment. So it's important that you can read from it, because if you could, like in regular code, if you could read from it, then of course, because you have this evaluator that can change over time, then your whole consistency flies out of the window. But as I said, it's actually, if you actually want to work with that, it's nicer to work with it if you just basically copy and emulate its behavior using metaprogramming. All right, so how does this work then? So what you do first of all is you have this in your meta environment. There is you have the collection of rules for your grammar, and oh sorry, I completely forgot. There's also a starting non-terminal in the meta environment. Of course, you need a starting non-terminal. Yeah. So what you do is you parse your input string from with this grammar that you've given, and you get a syntax tree for that grammar. And what you do now is you replace all let's say the tree is structured so that every node in the tree is annotated by the parsing rule you used to parse that specific part of the tree. Then you replace these annotations by the terms that correspond to them that you have in the meta environment. And then you basically fold over the tree and apply everything to what's below it. There's actually a nice categorical interpretation of what's going on there, where you can define a certain category for context-free grammars, and then this category will be isomorphic to a certain subcategory of your basically of your language, where parsing rules correspond to constructors, and non-terminals correspond to inductive types, certain inductive types. Well, you have this equivalence, which is nice, and then the only thing that basically moves away from this is that one can use this equivalence to get a bit of intuition, basically, but actually I just use any regular functor. Basically, what these rules in the meta environment are is specifying a functor from a certain category of context-free grammars to types and functions in the language. So now you have so when you did this, you have arrived now at the point where you have some value, or like a term representing a value, and what you do is you apply the evaluator to that resulting term, and then you type check that application, and check if it lives inside of the meta monad, and if it does, then you're happy, and you try to normalize this value, and basically because the meta monad, or because values in the meta monad will always normalize to this psi I've had before. They will normalize to xi, mu, or epsilon, but then depending on what happens, you can then go on and execute these actions, right? If you have an action in xi, then there's a concrete thing that you're supposed to do, and well, if you arrive at epsilon or mu, then you just basically continue on or do nothing, in a sense. Well, basically like you would expect. right? Yeah, and then at this point you've made some modifications, or you might have made some changes to your environment, and at some point you're done and wait for the next input. And that's actually how all input happens here. So there's no certain notion of like a top level syntax or anything. Every input, basically when it comes down to it, gets at some point reduced to just some value in the meta monad, and then gets executed. So all these let definitions and so on are also, they just at some point are values in this meta monad. Okay, and so to show a little bit how this works, I have a second demo here. So this is about natural numbers. So this is the file, well, it's actually the file defining natural numbers, but I left out a few unnecessary things that are still in the original file. So the way it works is that I have this this special notation for regular names in the environment. So when I so down here, the last line changes this this meta environment, or like updates it, let's say in this case. And one thing I'm doing is I'm specifying here the init namespace, let's say. It's called like that. And so what happens if I execute this command at that point? The system will look for all names in the environment that start with init and then a $sign. And then it tries to get the rules, or it tries to convert these into passing rules. So the first thing is just a namespace. But then up to the next $sign is the name for the non-terminal that we want this rule to correspond to. And then there's another $sign, and then you can put what this non-terminal should expand to. So in this case, for all the 10 digits, we have a rule, and then I said the things in the like the rules always consist of pairs of, well, an actual rule and a term, and well, the term is just what we're defining here on the other side of the equal sign. The type annotation here is, you could just leave it out. It doesn't do anything in that regard. And then there's one more special thing. What do you write if you want to refer to other non-terminals? And what you do is you encase it in underscores. So this tells you that I mean the non-terminal corresponding to dec digit. And in that case, and well, the next rule here is for dec prime, which is what we're just defining here. And like there's one more small thing, and there are a couple more technical things about escaping and one special case if you want to parse an arbitrary character, but that's basically the syntax. And so if you write this, for example, right now, then I haven't loaded this file, and you will just get an error message because it doesn't know what to do with 5. And so if we import it, and just for safety, I'm importing the the regular file, not the demo file here. Let's see, okay, a bunch of stuff happening. And now it works. And so here you can see how this, basically how this whole system works. If I want to pass this 5, so first of all, start down here at the bottom. We have a rule down here that tells you, well, if you want to pass a single term, there's 2 rules for terms depending on, because sometimes you need to put brackets. So I have 2 rules for terms. Yeah, if you want to pass a single term, you can pass it as like with the stack nut non-terminal symbol, which is defined here, that line. And what a deck nut is a digit followed by deck nut prime. And the reason why I have deck nut prime is because I don't want to allow empty strings of digits. So you have to parse a digit first, and then you can pass a deck nut prime, which is a possibly empty string of digits. So you can see that here we have deck nut prime can parse an empty string, or it can pass a digit followed by another deck nut prime. Okay, and then at the end we just pass the deck digit. And so let's see, we parse 5 here, so we get the symbol deck 5. You can find that here. Then we have parsed this using this rule previously. So for this we get the term const deck. That's this term, and we apply it to the deck 5. And then at the end we parse a deck nut prime, and because we don't parse anything here, we get this rule. So we get the empty list, and well, this is also just defined via metaprogramming. So this just leads to us to this nil. And then the remaining thing is we need to wrap this in a way to actually give us a natural number back, right? Because if we do this, this is just a list of deck at this point, right? So to convert this back into a natural number, I have a function deck to nut here and a function deck list to nut that basically do this conversion. And so at this rule where I'm parsing a natural number, I'm put this in a new line. I have to use quotation here. So I want to write the term deck list to nut applied to the list we've got, and so this theta is a quasi quotation operation. So this is quoted, and it's applied to whatever lives in here, and this gamma is an anti-quotation. And this is how this term is written at this point. And yeah, that's basically how this parsing thing works at the end. You go down your tree, parse all your things, and basically go back up and apply all the terms, and then you end up with a value. And that stuff is of course type checked later on, so you can't do anything that's not allowed. Yeah, that's basically how this works, and this is how you can do this like in a very small language implementation. All right. So what do I want to do in the future? There is a bit of, there's actually a lot of work to do. First of all, there are lots of temporary hacks that really shouldn't be there. If you want to clean this up. So as I said previously, that there's a bunch of unfinished things, a bunch of stuff that hasn't been implemented yet, and some of the stuff are some of the things I've built are very, very hacky. Like the notations for lists and so on, they are fine, but the module system, for example, and the the code generation for data type declarations is really messy. So that needs some refactoring and cleaning up. And of course, I need to improve performance. So I would say in general, performance is of type checking. Performance of type checking is kind of okay for the most part, but in the special case where you're defining something inside of a module using the module system, then it suddenly becomes very slow, which is probably because of some string concatenation issues. So maybe I just need to add built-in strings to the system to make this fast. I don't know what's precisely the problem here. Maybe it can also be fast without built-in strings. I don't know, but yeah, I think these are the culprit for the module system. But yeah, I think outside of the module system, I mean, it's not gonna win any records, but I wouldn't call it slow outside of the module system. Right, then of course more features. That's always the thing. I have a bunch of more of extra ideas that should be possible in principle, and of course there are a bunch of things that I mentioned previously that I haven't been implemented yet. So there's a lot of work to do there, and then there's of course the question of tooling. So I have like a very, very basic syntax highlighting mode for now, which is better than nothing. But of course there are very interesting questions regarding tooling, because like, how do you do syntax highlighting when you don't know what the syntax will be, right? So I think the general idea here is, of course, that you go through the system itself, where you would just provide a library that basically lets you do things like syntax highlighting and interaction with your text editor. Have it built in the system itself, and then basically just have a standard interface where whenever you update your syntax, it updates the stuff for you. And then you could, for example, imagine that you annotate parsing rules with syntax highlighting annotations that let you decide what should be highlighted and whatnot. So I think there are ways to go about this tooling issue, but yeah, I haven't really thought about it that much. All right, so yeah, if you stayed around that long, thanks for listening. If you want to support the project, I'm very happy if somebody wants to participate in any way, so writing documentation, just doing experimentation and letting me know if stuff doesn't work or is badly explained. That's always very helpful. And of course, if you want to write some meta system that I mentioned or something else, that would of course also be very helpful. And there are tons of things from very easy to probably very difficult that should be possible. And then there's of course this question about funding, which like I'm working on this right now completely in my spare time. I've got some funding from Statebox in the past, but that ran out at some point. So this is currently completely unfunded, sadly. And so if, I don't know, someone thinks like their university might be interested in funding something like that or whatever, that would probably be very helpful. So yeah, especially like at the current point in time where there are lots of open things that need to be done, and like I feel like if I'm like completely on this own in my spare time, then the progress will like become slower and slower, because there's just so much to do and not enough time. All right. So if you have any questions, you can ask me now. You can ask me, I guess, on the category theory Zulip chat or on IRC maybe, or you probably got also the link to Twitter. Not sure how much I get Twitter notifications, but I'll try to answer there as well. So yeah, I guess I'll wait a bit if there will be any more questions, then